So I want to talk about today is a very simple but also very useful inequality, and one that you'll see a lot come up in contest math. That is the AM-GM inequality. The AM stands for arithmetic mean, or the mean that you'll probably think of when you first hear the word mean. That's just the sum of n terms divided by n. And the GM part is geometric mean, which is similar, except it's the product of all the terms and taken to the nth root. And what the inequality part of this is just that the arithmetic mean is greater than or equal to the geometric mean. So to prove this, we're going to use a technique called Cauchy induction. And what that is very simple. It's two parts. So Cauchy induction. The first part is showing that this works for all even n's. So we're going to prove it for 2n, right? And we're also going to prove it so if we give an n and we're able to show that it works for an n, we also need to be able to prove that it works for n minus 1. And what this effectively does is allow us to prove, so step 1 allows it to prove this for even numbers. And step 2 allows us to prove it for every even minus 1 number, which is also just every odd number, right? So let's start on step 1, and that's going to be just proving the base case with two numbers. So a1 plus a2 is greater than or equal to the square root of 1a2, right? So let's just multiply by 2 and square both sides. And now 4a1, a2. And let's just expand the left. And you might already be able to see where this is going, but now we can subtract the 4a1, a2 term. So we'll have a squared a1 minus 2a1, a2 plus a2 squared. It's going to be greater than or equal to 0. And this simplifies to a1 minus a2, the whole squared, which is greater than or equal to 0, which must be true because it's a squared term. So it's only going to be positive. Okay, so now that we have that, the base case done, we can start to prove it for higher even numbers. So let's just pick 4 numbers. You have a1, a2, and a3, a4, and we're going to apply AM-GM, or at least the base case, to each of these, right? And is greater than or equal to the square root of a1 and a2. So now what we can do is we can actually take the mean of both of these sides, or more specifically, add up both of these inequalities and divide them by 2. So that's going to look like a1 plus a2 over 2 plus a3 plus a4 over 2 is greater than or equal to the square root of a1 and a2 plus the square root of a3 and a4 over 2. And this side simplifies very easily to a1 plus a2 plus a3 plus a4 over, so there's going to be over 2, but there's another over 2 here, so that's just going to simplify to over 4. And this side, what we can actually do is very clever. We can apply AM-GM to this side. So let's just do that here. So you have square root of a1, a2 plus the square root of a3, a4 over 2 is greater than or equal to the square root of a1, a2, and the square root of a3, a4 And once we multiply this, we're going to have the square root of the square root, which is just the fourth root. So it's the fourth root of a1, a2, a3, a4. And you can actually just substitute this back into the original expression. So we can substitute this over here. So that's this. So it's going to be greater than or equal to 4 a1, a2, a3, a4. That's the statement of AMGM here. And actually, none of this, we didn't actually depend on whether this was 2 or not. We realized that this could have just been any arbitrary n, and we've proved that it works for all 2n. Okay, so now that we finished condition 1, we can move on to condition 2. So for condition 2, what we're going to do is very similar for what we did with condition 1. We're going to make, well, actually, it's going to be a little bit different, right? We're going to make an expression like so. So let's say we have a1, a2, a3, all the way until an minus 1, and then we're going to add this again. So we're going to add the a1 through an minus 1, and I can actually make this a bit shorter. So plus dot 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 an minus 1 plus a1 plus a2 plus an minus 1 divided by an minus 1, or sorry, n minus 1, all over n. So there are n terms here, right? And actually this is all going to simplify very nicely, because if we try to make a common denominator with this, we're going to get n minus 1 times an, a1 plus a2 plus an minus 1 again over n minus 1. But you'll notice here we also have a1 plus a2 plus an minus 1. So this is going to cancel and turn into n. So you can just ignore that. But there's also an n down here. So these are going to cancel. And what we're going to be left with is just this, and a1 plus a2 all the way to an minus 1 divided by n minus 1. And AMGM, by the way, is still going to apply for this term. And so we're going to have a1, a2 until a1 plus a2 is going to be a bit tight over n minus 1, and take that to the nth root. So we can just copy that here. Oops. Okay. And here, what we can actually do is a bit clever. We can take both sides to the power of n. So that will remove that, and this is now to the nth power. But we can divide this from here, and this is going to turn into n minus 1. So what we're going to end up with, so there's going to be an n minus 1 there, and this is going to have the n minus 1th power, and then you might be able to see how we do it now. We take it to the n minus 1th root, and this is again the statement that we make in AMGM. And now we've proved the second condition, so now it's obviously possible for every single n that exists. Okay, so now that we're able to do this so now that we're able to understand why AMGM works, it's time to do some very basic problems using it. So this one is from the very first AIME, and it's number 9. So the problem just asks us to find the minimum of this expression at the top such that x is between 0 and pi. And we can just do some actually, before I solve it, you might want to take a minute to just pause and do the problem yourself. Okay, hopefully you're back. We can divide both sides by x sine x, just simplifying, plus 4 over x sine x. And this this looks very easy to do with AMGM because we have a number like the large term here, and we also have the large term in the denominator. So if we manage to somehow multiply these two terms, that would be great. And actually, because it's AMGM that we're going to use, we can. So this is going to be greater than or equal to the square root of 9x sine x times 4 over x sine x. X sine x is going to cancel out. 9 times 4, and that's going to be 6. So 9 sine x plus 4 by x sine x, or over 2. We multiply 2 to both sides, and this equals 12, or is greater than or equal to 12. And since they asked for the minimum, it's going to be 12, because the inequality that we're given says it's always going to be 12 or more. So the least it could be is 12. And AMGM is also very useful for optimization problems like this. So I'm going to be seeing a similar problem here from the British Math Olympiad from the year 2000. So we have the minimum of this expression, and what you might be able to, does that say 42? I think that's supposed to say 4z squared, sorry. So let's just rewrite it. So x squared plus 2y squared plus 4z squared plus 4xz, and we're given the condition that xyz is equal to 32, so that'll be helpful for later. Here we can use some convenient identities, so let's just rearrange it real quick. You have x squared plus 4xz plus 4z squared plus 2y squared. And here, some of you might recognize that this is a perfect square. So x plus 2z squared plus 2 times y squared. And here we can use AMGM on this. So we're going to get that x plus 2z over 2 is greater than or equal to square root of 2xz, and we multiply by 2. So x plus 2z is greater than or equal to 2 times the square root of 2xz. And we can substitute this back in. Since it's asking for the minimum, we obviously want to minimize everything that we can. So we're going to put this back in here, and when we square that, we'll get 8xz plus 2y squared. And now, if we just do AMGM on this, actually, let's just do that really quickly. We're going to get 8xz times 2y squared. We have an extra y term, and that's not very helpful to solve the problem. So what we're actually going to do is split up the 4xz term. So we're going to, or 8xz term into two 4xz terms. So it's going to look like this. Over 3, whoops, is greater than or equal to the cube root of 4xz times 4xz times 2y squared. And when we multiply all of this, we're going to have 4 times 2 is 32 times xyz, the whole thing squared. And we're given xyz, that's 32. Actually very convenient. 32 times 32 squared, and then you take the cube root, it's just 32, and we have 4xz. Actually, let's not bother writing it. We know that the minimum of this is going to be 32, but we want this part, so we just multiply it by 3. 32 times 3 is 96. That's our answer. And before you go, I just want to give you like one practice problem that you might want to do later. So this one is from the 2000 AMC 12, problem number 12. You want to check your answer. Just asking the maximum of AMC plus AM plus AC plus CM, A plus M plus C is equal to 12. So solve this and tune in next time for a video on Cauchy-Schwarz inequality. I'll see you then.